Let us discuss how dynamic programming method can be used to solve a linear programming problem. Consider the question, use dynamic programming to solve the following LPP. Maximize z equal to 3x1 plus 5x2 subject to x1 less than or equal to 4, x2 less than or equal to 6, 3x1 plus 2x2 less than or equal to 18, x1, x2 greater than or equal to 0. Now, we know the usual method of solving this problem by the usual simplex method technique. Now, we are going to adopt dynamic programming technique to solve this same LPP, which we solve usually by the method of simplex algorithm. Now, as you know, dynamic programming technique is to divide the given problem into various stages, and we will find optimal solution to each stage, and thereby we will find the final optimum solution. So that's a technique adopted in dynamic programming method. Now here you can see that there are three constraints. There are three constraints, and these three constraints are regarded as three stages. So these are the three stages. Now these three stages being represented by B1 equal to 4, B2 equal to 6 and B3 equal to 80. So we have three constraints, and these three constraints are actually three resources, and we have the stages associated with the three constraints as B1 equal to 4, B2 equal to 6 and B3 equal to Today, through this video, we are going to discuss how dynamic programming method can be adopted to solve a usual linear programming problem. So here we are given a maximization objective function, and it is to be maximized. This objective function is to be maximized subject to the three constraints. So let me read the question. Use dynamic programming to solve the following LPP. Maximize z equal to 3x1 plus 5x2 subject to x1 less than or equal to 4, x2 less than or equal to 6, 3x1 plus 2x2 less than or equal to 18, and the non-negativity restriction x1, x2 greater than or equal to 0. Now, when we have to solve a problem, whatever the problem is, when we have to solve a problem using dynamic programming, since dynamic programming technique is a multi-stage decision process, we are going to split the given LPP into different stages, and that stages depend upon the number of decision variables here. So let us discuss this in detail. So here you can see that there are three constraints. So here we have the three constraints, and hence we say that there are three states for this dynamic programming problem. So you know that for a dynamic programming problem we need stages and states. So here we have, with respect to this LPP that we are considering, there are three constraints, and these three constraints refer to the three states, and in order to refer to the three states, we make use of B1 equal to 4, B2 the second state, B2 represents the second state denoted by 6, and B3 represents the third state denoted by 80. Now we can see that there are two decision variables. And these decision variables denote the two stages. So we have two stages and three states for this dynamic programming problem. Now let us consider the solution. Actually, the solution of a linear programming problem through dynamic programming algorithm is a very simple technique. So let us see how this is proceeded. So we are going to start with x2 and the corresponding stage. So let us start with f2 x2. So we will proceed from f2 x2 and then we will move to f1 x1 and then we will find the ultimate optimum solution for the given linear programming problem. So let us get started with f2 x2. Now actually it is f2 b1 b2 b3, or to be specific this is f2 4 6 18. Okay, and this is the maximum of 5x2. See, here we are considering only one stage at a time. So here we are considering the second stage. We are going back from the second stage to the first stage. So let me take f2 as maximum of 5x2, and that maximum ranges over 0 less than or equal to x2 less than or equal to b, where B is the minimum among 6 and 18 by 2. B is the minimum among 6 and 18 by 2. 6 or 6 by 1, that comes from the second constraint. Then 18 by 2. 18 by 2 corresponds to the coefficient of x2 from the third constraint. So the minimum value is 6. So our B ranges from 0 to 6. So we can write this f2 as equal to maximum 5 into x2, 5 into maximum x2, and that 5 into maximum x2 can be written as 5 into minimum of 6 and 18 by 2, because the maximum possible value for x2 is a minimum among the possibilities. So only the minimum among the different possibilities satisfy the two constraints simultaneously. Hope the idea is clear. So the maximum of x2 is the minimum among the different possibilities. So hence we have 5 into 6 equal to 30. Okay. So hence we have the we have the second stage, which is actually considered first. Now let us get to the first stage. So now let us find our f1 4 6 8. f1 4 6 8 is maximum of, so we do have to consider both the variables here. So 3x1 plus 5x2. So we will reduce them to a function of a single variable. Now, so f1 4 6 8 is maximum of 3x1 plus 5x2, and this is equal to the maximum of 3x1 plus 5 into minimum of, or rather we can write it as 5 into, let us write it as a recursive equation, 5 into f2 of 4 minus x1. See, where does that 4 minus x1 comes from? So we are dealing with the variable x1. We are dealing with the first stage. And so from the first constraint, you can take it as 4 minus x1. From the second constraint, we can have just 6 because it doesn't have any x1. From the third constraint, you can write it as 18 minus 3x1. Okay. So we will write 5x2 as 5 into, so x2, the variable, decision variable x2 is dealt in the previous stage number 2, which is actually considered first, and from there our x2 is represented, x2 can be represented in terms of f2, so it becomes f2 4 minus x1 6 18 minus 3x1. So this f2 gets modified. This f2 gets modified to 4 minus x1 6 18 minus 3x1. Okay. Now so here as you can see throughout there is only one variable x1, and hence let us write the range for x1, 0 less than x1 less than or equal to a b. And let us see what that b is right now. B is equal to the minimum among 4 by 1, that is taken from the first constraint. Then from the second constraint you don't have any x1, so let me skip that, or otherwise you can write it as 6 by 0. Then 18 by 3. 18 by 3. So these are the three values, two values, and hence the minimum is equal to 4, and therefore our x1 ranges from 0 to 4. Okay, so let me write it in a better way. Maximum of 3x1 plus 5 into minimum of 5 into minimum of 5 into minimum of let us see what that expression is from the previous stage. 5 into minimum of, from the previous stage it is minimum of 6 comma 18 by 2, and hence here we should write it as 6 comma 18 minus 3x1 by 2. The previous stage function gets modified with respect to the variables that we have in the present stage. Hope it is okay for you. From the previous stage f2, we know that f2 is written as minimum 5 into minimum of 6 comma 18 by 2. Now here the expression f2 gets modified to 4 minus x1, 6, 18 minus 3x1. So here from the stage that we have considered first, we have to modify this 5 into minimum of 6 comma 18 by 2 with reference to the function that we had just now, and we will write it as 5 into minimum of 6 comma 18 minus 3x1 by 2. Okay, so this is how we write f1 4 6 8 now. Now let us see what these minimum values are. So we just had the recursive equations in order to solve this linear programming problem. Now let us try to see what these minimum values are, and hence we shall find the maximum possible value for Z. Okay, so let me write here. Let me find here the minimum of 6 comma 18 minus 3x1 by 2. Minimum of 6 and 18 minus 3x1 by 2. And this ranges over 0 less than or equal to x1 less than or equal to 4. The range of x1 is from 0 to 4. Okay, so let us see how this is proceeded. Now say for x1 is equal to 0. For x1 equal to 0, the two values are 6 and x1 equal to 0. For, it is 18 minus 3 into 0 by 2. So 6 comma 9, and the minimum value is 6. For x1 is equal to 1, we have the set getting reduced as 6 comma 18 minus 3 by 2. 18 minus 3 is 15 by 2 is 7.5, and still the minimum is 6. When x1 is equal to 2, the two values are 6 and 18 minus 6 by 2. 18 minus 6 by 2 is 12 by 2, that is 6. So both the values coincide, it is 6 and 6. Now for x1 equal to 3, for x1 equal to 3, we have 6 and 18 minus 9 by 2. 18 minus 9 by 2 is 9 by 2, and hence the minimum value is 4.5. And so this minimum value comes from the second part when x1 equal to 3. Okay, so for x1 equal to 4 also, definitely the minimum value will come from the second part. So let us conclude this. So there are two possibilities. One is the minimum value can be 6 when 0 less than or equal to x1 less than or equal to 2, and the minimum value is 18 minus 3x1 by 2 when 2 less than or equal to x1 less than or equal to 4. So we got this minimum value in the first case. Now let us proceed to find the second minimum value. Let us proceed to find the second minimum value. We are going to substitute and we are going to substitute this minimum value into 3x1. Let us proceed to find what is 3x1 plus 5 into minimum of 6 comma 18 minus 3x1 by 2. So substituting this minimum value here, we have 3 into 6 when 0 less than or equal to x1 less than or equal to 2. Sorry, it is 3 into 6, 3x1. Sorry, it is 3x1 plus 5 into 6. 3x1 plus 5 into 6 when 0 less than or equal to x1 less than or equal to 6. We are going to substitute our obtained minimum value into this expression, and hence we have 3x1 plus 5 into 6 for 0 less than or equal to x less than or equal to 2, and 3x1 plus 5 into 3x1 plus 5 into 18 minus 3x1 by 2 for 2 less than or equal to x1 less than or equal to 4. Okay, so we got 3x1 plus 5 into minimum of 6 comma 18 minus 3x1 by 2. Okay, now let us find our F1468. Now let us find our F1468. So F1468 is equal to the maximum of 3x1 plus, so that is equal to the maximum of 3x1 plus 5 into minimum of 6 comma 18 minus 3x1 by 2. Okay, now please listen here for a moment. Now the maximum value among 3x1 plus 30 and 3x1 plus 5 by 2 into 18 minus 3x1. Let us find the maximum value among these two expressions. So now you can see that 3x1 plus 30 has the range for x1 as 0 to 2. So definitely its maximum occurs at x1 is equal to 2. And that maximum value at x1 equal to 2 is equal to 36. Okay, now x1 equal to 2 is the lowest value in the second part of the function. And since x1 is subtracted in the second part of the function, the second part of the function will also attain its maximum when x1 equal to 2, because as you can see that this we will have minus 15 by 2 as minus 15 by 2 x1 as a coefficient of x1, and hence the value as x1 increases, the maximum value decreases. So obviously the maximum of the second part of the function is also 36, and that also occurs at x1 equal to 2, and therefore we can write this as 3 into 2, the maximum occurs at x1 equal to 2. So 3 into 2 plus 5 into minimum of 6 and 6. So this is 3 into 2 plus 5 into 6, and hence we have 36 as a solution. 36 as F1468. Now let me write the optimum solution. Optimum solution is x2 x1. So here we have got the optimum value for x1. x1 is equal to 2. The optimum value for x2. The optimum value for x2 is minimum of optimum value for x2 is minimum of 6 comma 18 minus 3x1 by 2. You can see that from here x2 is minimum of 6 and 18 minus 3x1 by 2. So here we substitute the optimum value for x1, and that optimum value for x1 is equal to 2. So whether it be 18 minus 3 into 2 by 2 or 6, the minimum value is 6, and hence we get the optimum value of x2 as equal to 6, and therefore maximum Z is equal to 36. So this is the optimum solution for the given linear programming problem. So once again, let me go through the whole problem. Here we are asked to solve the linear programming problem with the help of dynamic programming technique. Now in dynamic programming technique, we know that there are the problem has to be splitted down into various substages. So here the number of stages is determined by the number of decision variables. So since we are having 2 decision variables, the number of stages is equal to 2. And so we have to consider both stages. We will deal with stages one by one. Now in this particular problem, I am starting from the last stage and moving forward to reach the first stage, and hence the optimum solution. So we start with F2, B1, B2, B3, and you can see that B1, B2, B3 are the right hand side of the 3 constraints. They actually represent the 3 states of the dynamic programming problem. So F2, 4, 6, 8 is maximum. So in the stage 2, we are considering the decision variable 2, therefore maximum 5x2, and this x2 can range over 0 through 6, because B should be the minimum among 6 and 18 by 2, which is equal to 6. So therefore this maximum 5x2 is nothing but 5 into minimum of 6 and 18 by 2, because this minimum value satisfy both the constraints simultaneously. If you take the maximum value, that need not satisfy the second constraint. So that is why we take the minimum among the different possibilities. So hence we have 5 into 6 equal to 30. Now we go for the first stage, F1. So this is our first stage, F1 4, 6, 8, and that is maximum of 3x1 plus 5x2. The whole objective function is considered, which is maximum of 3x1 plus 5 into. So this is the recursive equation form, F2 4 minus x1. Now since we are concentrating on the first decision variable, we have to write it as 4 minus x1, then 6, then 18 minus 3x1. And this can be written as maximum 3x1 plus 5 into. So this F2 is already considered in the previous stage, so that F2 is nothing but 5 into minimum of 6, 18 minus 3x1 by 2. So here we have 18 by 2, so that should be modified as 18 minus 3x1 by 2. Okay, so we have formed the stages, and now the only thing that is left is to find the minimum value, and then hence that substituted into this F1 will give you the optimum policy. Okay, so that minimum value is obtained. So this is simply an algebraic calculation. Just find out the possible set of values for which the 6 is minimum, and find the possible set of values for which 18 minus 3x1 by 2 is a minimum. So we obtain that here. So these are the possible values, possible minimum values when you substitute the whole set of values from 0 to 4. And then once you obtain that minimum value, we will substitute that minimum value into this expression, maximum into the expression 3x1 plus 5 into minimum of 6, 18 minus 3x1 by 2, and hence we will find the value to this particular expression. So hence we obtain the value in this particular way. Now we proceed to find F1 468. F1 468 is the maximum of this 3x1 plus 5 into minimum of 18 minus 3x1 by 2. So you can see that this 3x1 plus 5 into a minimum of 6 and 18 minus 3x1 by 2 attains a maximum value at x equal to 2, at x1 equal to 2. At x1 equal to 2, 3x1 plus 30 attains its maximum value. Similarly, at x1 equal to 2, the second part also attains its maximum value, and hence we have the maximum value here, and the maximum value occurs at x1 equal to 2. So that x1 equal to 2 is taken as the optimum value for x1, and with x1 equal to 2 we proceed to find x2. We know that x2 is equal to minimum of 6 and 18 minus 3x1 by 2. x2 is minimum of 6 and 18 minus 3x1 by 2, Hence we substitute x1 into this expression so as to get x2, and hence we have the optimum solution as z equal to 36. So hope you understood the problem. Thank you.